On May 21st, 2026, SpaceX is attempting to launch something that has never existed before in the history of rocketry. And most people have absolutely no idea what they are about to witness. This is not another test flight of the same rocket with a small patch or a minor tweak. Starship version 3, also known as Flight 12, is a complete ground-up redesign, a machine so different from everything that came before it that engineers at SpaceX refer to it as a step change, not an iteration. And it is launching right now, in the same week you are watching this. So let us slow down and actually understand what this rocket is, why it matters on a scale far beyond space nerd territory, and why a successful launch this week could be one of the most consequential events in modern aerospace history. First, let's talk about what SpaceX just built. Starship V3 stands 408 feet tall when fully stacked. That is the combined height of Booster 19, the super heavy first stage, and Ship 39, the upper stage that sits on top of it. The full vehicle is approximately 1.5 meters taller than its predecessor. Version 2, it is the tallest rocket ever assembled and prepared for flight. But height is the least interesting thing about it. The super heavy booster on V3 is powered by 33 Raptor 3 engines. Every single one of them is a brand new design. Together, those engines produce approximately 18 million pounds of thrust at liftoff. That number is worth sitting with for a moment because it requires a historical comparison to fully appreciate. Saturn V, the rocket that sent human beings to the moon in 1969, the machine that remains one of the greatest engineering achievements in all of human civilization, produced 7.5 million pounds of thrust. For over 50 years, that was the gold standard, the thing that defined what big meant in rocketry. Starship V3 produces more than twice that. Not slightly more, not incrementally more than double on a rocket that is also designed to be completely reusable. NASA's Space Launch System, which cost over $23 billion to develop and flew its first mission in 2022, produces 8.8 million pounds of thrust. Starship V3 outpunches it by a factor of 2. And unlike SLS, which is expendable, meaning it is destroyed on every single flight, Starship is being engineered to fly again and again within hours or days of landing. The Raptor 3 engine is where the real story begins, because this engine is not an upgrade to the Raptor 2. It is a clean sheet redesign. SpaceX engineers went back to the drawing board and rebuilt this engine from the inside out with one overarching goal: make it simultaneously more powerful, lighter, simpler, and cheaper to manufacture. The sea-level Raptor 3 now produces 551,000 pounds of force per engine, up from 507,000 in the previous version. The vacuum variant over 606,000 pounds. Every single one of those engines on the booster is now a Raptor 3, making this the first fully Raptor 3 equipped Super Heavy ever to reach a launch mount. But the number that matters more than raw thrust is what SpaceX did to engine weight. Each Raptor 3 weighs approximately 1,525 kilograms, more than 100 kilograms lighter than the Raptor 2. When you multiply that mass savings across all 33 booster engines, you are reducing the dry mass of the first stage by over 3 metric tons through propulsion alone. In rocketry, every kilogram you remove from the dry mass of a vehicle translates directly into payload that can go to orbit. The external architecture of Raptor 3 also looks completely different. SpaceX eliminated the external gas generators and external plumbing that made previous Raptors look like a tangle of pipes and tubes. The new engine has a clean, internalized design. Sensors and controllers built directly into the engine body. No external shrouds, no visible maze of lines. It looks almost impossibly simple for something producing that much power. This design philosophy of radical simplification, which SpaceX has applied across the entire V3 vehicle, is not just aesthetic. Simpler means fewer failure points. Fewer failure points means higher reliability. Higher reliability means more reuse. And more reuse is the economic foundation of everything SpaceX is trying to build. When SpaceX went from Raptor 1 to Raptor 2, the company cut engine manufacturing time from 11 days per engine to just 1 day. With Raptor 3, automated precision welding, robotics, and advanced 3D printing are pushing production speed even further. SpaceX has said it is building Starships at a rate of roughly 1 vehicle every 2 to 3 weeks. That pace of production is simply not comparable to anything else in the history of large rockets. Now, let us talk about what V3 can actually carry, because this is where the implications become truly enormous. Starship V3 is targeting a fully reusable payload capacity of over 100 metric tons to low Earth orbit. In expendable configuration, where the vehicle is not designed to return, that number could reach 200 metric tons. To put that in perspective, version 2 of Starship was targeting around 35 metric tons in the same reusable configuration. The jump from 35 tons to over 100 tons is not an incremental upgrade. That is nearly a 3 times increase in payload capacity with a fully reusable vehicle. No rocket in history has ever combined this level of payload capacity with full reusability. The systems that exist today, the Falcon 9, the Falcon Heavy, the SLS, the Vulcan, either carry much less, cost far more per flight, or are expendable. V3 is attempting to make all of those trade-offs obsolete in a single vehicle. The V3 upper stage, Ship 39, has been redesigned in nearly every subsystem. The propellant tanks have been enlarged to carry more fuel. The aft section has been simplified, with engine shrouds deleted and fluid and electrical systems rerouted for a cleaner, more efficient layout. The flap actuation system, those large control surfaces that steer the vehicle during re-entry, has been completely rebuilt. Instead of the previous dual actuator system, V3 uses a single actuator with 3 motors per flap. That means the flap can still function correctly, even if 1 or 2 motors fail, which is a significant reliability improvement, especially during the violent thermal and aerodynamic loads of atmospheric re-entry. The avionics have been upgraded with custom units, multi-sensor navigation, and high-bandwidth Starlink connectivity. Energy storage systems have been improved, and for the first time, Ship 39 features docking adapters, 4 docking drogues, and dedicated propellant transfer connections that allow one Starship to physically dock with and refuel another in orbit. This is not a minor feature. This is the linchpin of SpaceX's entire deep space architecture. The reason orbital refueling matters so much is simple. Starship needs enormous amounts of propellant to travel beyond Earth orbit, to the Moon, to Mars, and eventually further. Carrying all of that propellant from the ground on a single launch is physically impossible given current rocket economics. But if you can launch a tanker Starship into orbit and then dock a crewed or cargo Starship to it and transfer propellant before the journey, you can effectively multiply the mission capability of the vehicle without needing an even bigger rocket. V3's docking hardware makes that tanker mission possible for the first time. Flight 12 will also test several new objectives that previous Starship flights never attempted. During the suborbital arc, Ship 39 will deploy 22 simulated Starlink satellites, mock-ups the same size as SpaceX's next-generation broadband satellites. The final 2 of those mock satellites are equipped with cameras that will scan Starship's heat shield and transmit imagery back to operators on the ground. This gives SpaceX its first real-time look at how the heat shield is actually performing from an external vantage point during flight, a capability that does not exist on any operational spacecraft today. Ship 39 will also attempt to relight one of its 6 Raptor engines while in space, a direct demonstration of the deorbit burn technology that future missions to the Moon and Mars will depend on. The ability to restart an engine reliably in the vacuum of space after the thermal shock of launch and the cryogenic environment of a long coast phase is a critical demonstration that has significant engineering complexity. Launching from a completely new facility adds another dimension to this flight. Flight 12 will be the operational debut of Starbase's Launch Pad 2, an entirely new launch complex constructed alongside the original Pad 1. Pad 2 features an upgraded propellant farm with increased storage capacity and faster pumping speeds. The launch tower's chopstick catch arms have been rebuilt with electromechanical actuators replacing the previous hydraulic system, making them faster and more reliable for booster recovery operations. Because this is the first flight of a significantly redesigned vehicle, SpaceX made the deliberate decision not to attempt a tower catch of the booster on this mission. Both stages will end their flights in water, a choice that prioritizes maximum data collection over hardware recovery. On a debut flight of a new design, there's more value in understanding exactly how the vehicle performed across the entire envelope than in trying to catch a booster that has never flown before. This is the same conservative approach SpaceX has used on previous first flights of major new configurations. The stakes surrounding this launch go far beyond SpaceX's own missions. NASA's entire Artemis lunar program depends on Starship working. The Starship human landing system, the vehicle that will carry NASA astronauts to the surface of the Moon as part of Artemis IV in 2028, is essentially a modified version of the V3 upper stage. NASA cannot realistically... Elon Musk has stated directly that V3 should be capable enough for initial uncrewed Mars missions, the 5 ships he wants to send during the November and December 2026 Earth-Mars transfer window, carrying Tesla's Optimus robots and early infrastructure cargo. Without V3 performing as designed, that already aggressive 2026 Mars launch window becomes effectively unreachable. Every week of delay in validating V3 erodes the margin available for Mars mission preparation. There is also the IPO dimension. SpaceX is targeting a NASDAQ public offering as early as mid-2026 at a valuation of approximately $1.75 trillion. Musk's compensation package ties 200 million shares to SpaceX, reaching a $7.5 trillion valuation and helping establish a permanent Mars colony of 1 million people. A successful V3 launch is a demonstration in front of the entire investment community that the technology underpinning those projections is real and advancing on schedule. A failure or a major anomaly, by contrast, would send a very different signal to the market at a very sensitive moment. It is worth stepping back and putting all of this into historical context, because the magnitude of what is happening right now is genuinely difficult to process through the lens of routine news cycles. The Saturn V was built by 16,000 engineers and 100,000 contractors over a decade, at a cost equivalent to roughly $150 billion in today's money. It flew 13 times across 6 years and then retired. It was never reused. Each mission consumed the entire rocket. The cost per kilogram to orbit for a Saturn V mission was extraordinary, and that extraordinary cost was precisely why the United States stopped going to the moon after 1972. Economics made sustained access to deep space impossible. Starship is being built by a private company in a factory in South Texas, iterating at a pace that NASA's government contracting model structurally cannot match. 5 flights in a single year, which SpaceX achieved in 2025, was more integrated Starship flights than the entire Saturn V program managed in its first 2 years. The reusability targets for V3, if achieved, would reduce the cost per kilogram to orbit by an order of magnitude compared to any existing heavy-lift rocket. An order of magnitude means 10 times cheaper, not slightly cheaper, 10 times. At that cost structure, missions that are currently economically impossible become routine. The construction of large space stations becomes affordable. The deployment of massive satellite constellations becomes trivially cheap. The resupply of a Mars base over multiple years of transfer windows becomes something a private company can finance without government backing. And the delivery of 1 million tons of cargo to Mars, the amount Musk says is needed to establish a self-sustaining colony, shifts from a multi-century project to something potentially achievable within a single human lifetime. None of that happens without V3 working. And V3 working starts with Flight 12, launching this week from a patch of scrubland on the Texas Gulf Coast. Whatever you think about Elon Musk, whatever you think about the politics or the timelines or the audacity of the claims, the rocket is real. The engines are real. The fire from 30 of 3 Raptors igniting simultaneously produces a shockwave you can feel across the Rio Grande. And the number those engines produce, 18 million pounds of thrust, is not a promise or a projection. It is a verified measurement from a static fire test completed earlier this month. The most powerful rocket in history is about to fly. Pay attention. And if this launch succeeds, if those 33 Raptor 3 engines light cleanly, if the stages separate on time, if Ship 39 deploys its mock satellites and restarts its engine in space and comes down in the Indian Ocean in one piece, then something shifts. Not just in a NASA spreadsheet or a SpaceX investor deck. Something shifts in what humanity actually believes is possible, because the history of exploration has always moved on the back of the machines that could carry the weight. And right now, that machine is sitting on a launch pad in Texas, loaded with propellant, waiting for a signal.